Enthalpy of turbomachinery. So we'll see the enthalpy change in compressor, process turbine, nozzle, diffuser, and heat exchanger. Little bit about the enthalpy energy. Enthalpy energy is associated with pressure and temperature of the gas. Enthalpy energy is equal to summation of internal energy and the potential energy or pressure energy. Internal energy represents energy associated with the temperature, and pressure energy represents the pressure energy associated with the pressure. So enthalpy will be high if the pressure and temperature of gas are higher. Mathematically, it can be written as enthalpy is equal to internal energy plus pressure energy. Enthalpy energy is also defined in most popular form as a product of a specific heat capacity at constant pressure and change in the temperature. If T1, T2 are the two thermodynamics points and average specific heat capacity at constant pressures is Cp, then change in enthalpy energy between these 2 points is expressed as in compressor and turbine. Enthalpy rise in compressor is H is equal to small h2 minus h1 is equal to Cp into T2 by T2 minus T1. In enthalpy drop in turbine, H is equal to H1 minus H2 because H1 is higher than H2, and Cp into T1 minus T2. Enthalpy rise in compressor. Compressor consume power for pressurizing the gas from low pressure to high pressure. Prime mover like motor and steam turbine are used for a drive of the compression. Enthalpy rise in compressor is a process 1 2 represents in enthalpy rise, that is T1 T2 is the process 1 and 2 represents energy imparted to the compressor. Other process are workhead process or standard reference processes, but actual energy or actual enthalpy given to compressor is 1 and 2 or T1 T2 process. Enthalpy rise represents in compressor input power by the driver. Enthalpy rise is calculated based on the inlet outlet process pressure and temperature of gas. Enthalpy rise can be static enthalpy and stagnation enthalpy. It is expressed as static enthalpy TA actually HA is equal to H2 minus H1 or Cp into T2 minus T1. In terms of stagnation pressure, this can be expressed as stagnation enthalpy rise. HAO is equal to H2 minus H1 plus half of V2 square minus Vn square, or stagnation enthalpy rise HAO is equal to H2O minus H1O, where HAO is a static stagnation, a small h1 H2 is static inlet outlet enthalpy, H1O H2O or stagnation inlet outlet enthalpy, T1 T2 are inlet outlet temperature, V1 V2 is inlet outlet velocity, Cp is average specific heat capacity at constant pressure. Enthalpy drop in process turbine. Process turbine produce power after taking energy from the high pressure gas during expansion process. So enthalpy drop processes 1 and 2 or T1 T2 process is a isentropic enthalpy drop process. This is ideal. An actual enthalpy drop T1 T2 or 1 2 process is actual process or actual enthalpy drop. Efficiency of turbine is 1 and 2 energy, that is enthalpy drop divided by enthalpy drop of 1 and 2 S or T1 T2S process. Enthalpy drop in process turbine. Isentropic enthalpy drop is considered as an ideal enthalpy drop without any losses. Isentropic enthalpy drop Hs is equal to H1 minus H2S. A static enthalpy drop is a difference between inlet enthalpy and outlet enthalpy of turbine, which is expressed as actual enthalpy drop H1 minus H2. A stagnation enthalpy drop is summation of static enthalpy and velocity head, that can be written as stagnation enthalpy drop HO is equal to H1 minus H2 plus half of V1 square minus V2 square. Stagnation enthalpy can also be expressed as stagnation enthalpy drop in the process turbine HAO is equal to H1O minus H2O, where HAO is a static stagnation enthalpy, H1 H2 is static inlet outlet enthalpy, H1O and H2O is a stagnation, inlet and outlet enthalpy. V1, V2 are inlet and outlet velocity. Enthalpy drop in nozzle. Design of the nozzle is such that the inlet cross-sectional area is a much more than outlet cross-section area, and because of this velocity increases. Increase in velocity causes decrease in pressure, and so hence enthalpy and so drop in enthalpy. Nozzles are used in process and steam turbine for impulse purpose. Nozzle is used to increase the velocity, and due to this enthalpy is dropped. This is expressed as enthalpy drop H is equal to half of V2 square minus V1 square, where H is enthalpy drop in joule per kg, V1 V2 are velocity at inlet outlet. Enthalpy rise in diffuser. Design of diffuser is such that inlet cross section area is much less than outlet cross section area, and because of this velocity decreases. Decrease in velocity causes increase in pressure and hence increase in enthalpy. Diffuser are used in compressor for pressure rise. Diffuser is used to decrease the velocity, and due to this enthalpy is increased, and this is expressed as enthalpy rise is H is equal to half of V1 square minus V2 square, where H is enthalpy rise, V1 V2 are velocity at inlet outlet. Enthalpy change in heat exchanger. Heat exchanger heat is exchanged between two gases in heat exchanger. One fluid gives heat, another fluid takes heat through the tubes and fin surfaces, and this is constant pressure process, and hence no work is done. In heat exchanger, heat is added to one fluid and removed from another fluid. Enthalpy increases when heat is added to that fluid and decreases when heat is removed from the fluid. The heat energy is exchanged is equal to in change in enthalpy. So heat in transfer Q is equal to H2 minus H1 or Cp into T2 minus T1, where Q is a heat transfer. H1 is to inlet outlet enthalpy, T1 T2 inlet outlet temperature. So hope you understood about the enthalpy change for the compressor, enthalpy change for the turbine, and enthalpy change for nozzle, diffusers, and heat exchangers. So thank you for watching.